kind introduction, and thank you also for inviting me to talk at this lovely event here. So indeed, Bernd has somehow prepared the floor because he stopped in the end with what you have to do with the data, and I want to give you an idea of how we can use artificial intelligence to analyze these data in sports medicine. And so it is already in use, artificial intelligence, and I would like to take a step back and look at where are we standing, where are we going, what needs to be done. So this slide now somehow is superfluous because Bernd has said it all and in a much better way than I would be able to do it. So yeah, data collection via new technologies. We have just seen that this is a huge ongoing trend, that there are many new things coming up thanks to the wearables. And definitely I don't have to explain what wearables are. Yeah, here this is just as a brief recap, but let me just go directly to the aim, which is that with the aim of the data that we gather from these wearables, we wish to be able to improve the health of the athletes, but also of recreational athletes, not just for professionals, also for recreationals, of course. And in the end, this will also lead to an improved sportive performance. So it is here that the wearables give us a huge amount of data. The term big data is no secret nowadays. We hear it all over and all over and all over. Though the trend has become a little bit less, it was huge 5 years ago. Like whenever you wanted to get some research money, you had to put big data in your grant, and then you were well off. You had a big chance to get the money. Nowadays, people have recognized, okay, everybody has done this, so we know that big data, they exist, and we have to find good ways to analyze them. So how can we do this? It's indeed a huge amount of data. How do we do this in a very efficient way? And it is here that artificial intelligence comes into play. Definitely, I would say that artificial intelligence is one of the biggest achievements in scientific research over the past years. And this is still going on. We talk nowadays about self-driving cars, which are still not yet there, but there is development to achieve this. We have probably also heard about the fact that computers nowadays become unbeatable in games like chess and Go, which in the 90s there was the first computer that was able to compete with the then chess champion. Nowadays, the chess champions, they stand no chance. It has become so much better that artificial intelligence is just taking over. Or to take a completely different example here from Luxembourg, in our Philharmonie some years ago, there was a song that was played, and this song has had as composer an artificial intelligence. So it was a song not written by a human, but by an artificial intelligence that has learned how a song is good, what do humans like. And it has been played here in Luxembourg. So this shows the developments that are taking place in artificial intelligence. And there is also more and more a trend towards using AI in injury prevention. Also more generally in medicine, but here we are focusing on injury prevention in particular. However, this, differently than in other domains, this research is still in its infancies. There are more and more studies that are doing this, but many studies don't do it in the best possible way. And compared to what is out there in other domains, it is really only in the starting. And so what we did is we made, together with Romain Zeil, that I think most of you, or not all of you know, and Thomas Tischer, and my PhD student Hans van Eetvelde, my former postdoc Luciana de Michelis Mendonça, we made actually a systematic review to check what is out there in the research world, what has been done in machine learning methods for sport injury prediction and prevention. And there, we found that not so much is out there of really high level. And so one aim of this talk is to really give a further motivation why we have to really launch this research, why we have to invest into this in order to be able to fully exploit what Bernd and other people are producing in terms of wearable data. Let me briefly say what is actually AI, because we all have heard of it, but mostly we don't have a very concrete idea what an AI is and how it works. In, I would say, 60% of the situations, whenever we talk of AI, this actually means machine learning. That is, the machine learns something from data and is then able to use it on its own to become smart on its own. It learns from the real world and then can use this on new data. to explain you this, I used a very simplistic representation. Let's move into the world of computer science, because in the end, it's all with algorithms that this works. What is the difference between machine learning and traditional programming? Well, in traditional programming, we have data and we have some program as input. And both of them give us an output. Very simple example, calculating the square root. My input, my data there is 49, for example. My program is calculating the square root. I get as output 7. Very easy. Our calculators are all able to do this. That is traditional programming. With machine learning, it's different. We have as input data and actually the result that is linked to our input. And then the machine is the one that has to search for the best program that links the two. This is the idea. So for instance, if we had 49 and 7, it is the machine that would have to see, oh, the program that does this is taking the square root. And this is exactly what we also want to do with injury prevention. We have some data, like data that we get from wearables, but also from questionnaires or biometric data. We know athletes, they have been injured or not. So this is our input. The different parameters plus the result, injury or not. And it is up to the artificial intelligence to find how can we make a link between the predictors, between the parameters, and the outcome being injured or not. So I already said this briefly. What is in injury, in sports medicine, we have two types of outcomes, let's say. Either the simple version, yes, no, with respect to an injury. In that case, we call this a classification problem. We want to be able to say, yes, there will be an injury, no, there won't be no injury. A second way of looking at an output could also be the degree of an injury. So if we have some scale on which we can say the injury is of this, or this type, potentially even a continuous scale, then, well, we want to predict a number, no more a category, but a number, and in that case it becomes a regression problem, just to settle the terminology here. What type of inputs do we have? Well, the inputs can be very diverse, which is one of the big difficulties in sports medicine. We have very different types of input. This can range from orthopedic risk factors to training forms. Nutrition comes into play, the fitness. We also have questionnaire data, and then of course we have the wearable data. Questionnaire data reflecting the psychological state. Wearable data that can be a continuous time measurement. And we already see here, on the one hand side, we have fixed scales that come from a questionnaire where we know, okay, to these are the answers, the one-time answers of this person. On the other hand side, with wearables, we have real-time data that comes in. And it is very difficult to combine this in a smart way within an AI. And that is one of the difficulties in sports medicine, to use AI to analyze the data. That is where this diversity of the input is, on the one hand side, its richness, and one of the biggest achievements that are possible when we are able to build a good AI, but also one of the big challenges. So to discuss this in a good way, let's see, how does an AI work? So I said machine learning, we learn from what we have. So for the data that we have available, we know for each input, as I said, the output. To these parameters of an athlete, we know whether or not the athlete has had an injury. And from this, the AI then learns. The term here, it's actually nice in sports, where we also have sports training, but also the AI is said to be trained on our data. That's also why we often use the word training data. So we train our AI. The AI learns to establish the links between the input, the parameters, and the output, injury or not, or degree of an injury. Now, at this point, this might not sound, for some people who are already working for some time in this field, this might not sound very revolutionary, because there are old statistical methods that do exactly this. So what is new here? Think of linear regression. Linear regression is one of the most basic statistical tools that you learn in your statistics classes, where you say, okay, this is my output, and my input depends in a linear way on this output. That's exactly the same. We have output, input, and the relationship. So what is the difference? What brings AI that is novel as compared to the statistical methods? Well, if you're not accustomed to working in this area, indeed the boundary between the methods can seem very blurry. And in our article here, we try to explain the difference. And I also try to explain this difference to you so that you not say in the end, okay, but this already exists. Why do we need to work on AI? So here I'm just trying to explain in simple words the main differences between statistical learning and AI. And no worries, I'm not going to explain how random forests, neural networks, or support vector machines work. This would be way too technical. That's not the goal. I try to explain it in simple words. So basically, in statistical methods, what we do is the following. We say, this is our output, this is our input, and we impose ourselves what is the link between them. Like in a linear regression model, we say the output depends linearly on the different input parameters. And then, well, from our data, we have to estimate the model, but we say ourselves, we believe that the relationship is linear. Or in logistic regression, there is another type of relationship. But basically, with statistical methods, it is the user in the beginning, the person who does the analysis, that chooses, this is how I believe the relationship to be. And then the exact model is estimated from the data. So this has one drawback, which is that we have to impose how we think that everything goes. And especially if you have a lot of parameters, this is a big choice to make. And it can be very restrictive. An advantage of this is that in the end, since we chose ourselves the model, it is easier for us to understand the outcome. That's an advantage of statistical methods. You can very well interpret the results. You can say, oh yeah, if this parameter changes by so and so much, then it will have this and this impact on the output. That's an advantage of statistical methods. So ease of interpretability, but restriction because we are imposing ourselves the model. In AI, it is exactly the other way around. In the AI, well, we have to go for one of these very general algorithms, but there is no model that we really impose. It is the AI that builds the algorithm from scratch, from the data. The AI searches for the links between output and input. So it is in that sense more general because we are not imposing ourselves the type of model that we want to use. That's the big advantage. And also it can deal with much bigger and more complex data sets than the statistical methods. However, one drawback that most of these methods have is they are black boxes. Very often when you're dealing with AI models or machine learning models, then in the end you get a result which is very, very precise, but it is because you did not set up the model has learned relationships, you cannot see in how far a small change in this input has this and that impact on the output. So it is not interpretable. I will come back on this later on because there is a big research going on about explainable AI or interpretable machine learning, where precisely the goal is to reuse these black boxes but make them interpretable. And that would be an ultimate goal because then you could use somehow the power of both domains. So now we know a little bit the difference between AI and statistical methods. Can we see if an AI is doing good or not? Well, typically, we measure the performance in the following way. So we have our data set on which we want to make our AI work. And what we do is we split it in two parts, a training data set and a so-called test or holdout data set. Why do we do this? Well, because we wish to train our AI on the so-called training data set and then evaluate it. I'm explaining the evaluation in the next two lines. And then evaluate it on these new test data. Why do we do this? Well, because if we use all of our data for training our model and then also we use the same data to evaluate how good, how precise our AI is, it would be cheating. It would be like a self-fulfilling prophecy. The AI has been trained to be ideal on these data, then of course it will have a very good performance if we evaluate it on the same data. And that's not the goal, because we would overestimate its performance, and then if in the real world new data come in, this might not work so well. This is why we make this training and test split. So for regression models, when we have like the degree of an injury, there the evaluation is done by looking, okay, the AI predicts this level of this degree of injury, in reality it was this degree, so we look at the deviation between the two values. For classification, yes, no, well there it's even easier, we just look at the percentage of correctly classified test data. So in how many of these available new data, in what percentage of cases did the AI correctly say whether the athlete has been injured or not? If this is close to 100%, we would be super happy, of course. What is very crucial here, and I really want to underline this because that's a mistake that we often found during our systematic review, the training and test data, they must be independent. So I think you got when I explained before why you cannot use the same data to evaluate and train your model, but it's even very strict. You have to really separate them because otherwise there is information leakage. So we have heard very often now the word leakage in the press, and here it would really be information leakage that could happen and would again falsify our performance of the AI. So this is very important. And of course, a word of caution. Obviously, the bigger and better our data set, the better our AI will also work. If we have bad quality data, then don't expect your AI to give you really good results. And this is especially so if we have a bad balance between the possible outcomes of in our training sets. So suppose that we have a training data set in which 99% of all athletes do not suffer from an injury. Of course, we hope for the athletes that this is the case, but then you have trouble to train your AI well, because if nearly all of our athletes remain healthy, well, then the AI will of course be tempted to always say, okay, nothing is happening. That's also something that you have to pay attention to. Whenever you train an AI, it should be somehow balanced. And if it's like 80 to 20% or 70 to 30%, then you can use methods such as over and under sampling, which means that from the majority class you take some observations out, or from the minority class there are nice techniques to somehow oversample this, which is to create artificial data that resemble very much those 30% of injuries that we have, such that we can use this as further input data. This is possible. It's not possible if you are 99% against 1%, then you can simply forget about it. But if you are 80-20, then you can use these techniques. A further word about training and test sets. Stratification is important. What does stratification mean? It is related to a little bit what I said here. Stratification means that there is a similar ratio of yes-no responses in our training and in our evaluation test set. Because of course, if we simply made the split between training and test set, and in the end, so we don't pay attention, in our evaluation, in our test set, there are only healthy athletes, but then of course, our evaluation will also be falsified. So we have to pay attention to that. I'm underlining again the independence between both sets, because sometimes we have to do data pre-processing, such as for instance standardizing, how we subtract the average to have data that all give us are on the same scale, for instance. We divide by a general average, we divide by a general variance to standardize our data. If we do this, we should only use this by means on the training data. Basically, bear in mind, everything that you do on your data to standardize or to work on it, it has to be on the training part. The test part has to be seen as future new data. You cannot use this at any point except for the evaluation. And yeah, as I said, in this paper we noticed that there were commonly made mistakes of that nature that led to an overestimation of the performance of the AIs. And this is the last point that I want to talk about. I had mentioned it before, the interpretability. Most AIs are black boxes. So they give a very good prediction, but it is impossible afterwards to explain how we got to this result. We just know somehow we get to this result. The result is nice, yes or no, but we don't know what are the main driving factors. That's of course a problem, because especially in sports medicine, you want to know what are the main risk factors for an athlete to suffer from an injury. That's what we have to know. And this is why interpretability is needed, and why explainable AI and interpretable machine learning are currently under investigation. There is a hot trend to improve the AI by adding these interpretability components. And here, I just would like to show you what this can look like. So for this example here, I really move out of the world of sports medicine. This was an artificial intelligence that we had written in the year 2018 to predict the World Cup 2018. And so basically we have trained it. There were various parameters that we took for every country into account, such as the age of the players, how many Champions League players were there, what is their ELO FIFA ranking, because that's the ranking of the national teams, or how old is the coach, how long has the coach been working, and also a new factor that we have developed ourselves, which measures the ability of every team. So we trained our AI, and then in the end, we made some interpretability by that looks like this. This here actually, what you can see here is for every parameter, you see how much the performance of the AI would decrease if we left each of these parameters out. And so you can see, here you see the mean decrease in accuracy. If we left out, for instance, this one here, there would be a 15% decrease in accuracy of our AI. So this is a very strong predictor. Same for ELO, rank, and so on. There are even some negative predictors, such as population, which basically means if we left the population size of a country out, for soccer, we would have done a better prediction. There are countries like China that are very bad, countries like Iceland that are very strong, so population size can be misleading. Luxembourg is not among those countries that would be misleading. We would be fully helping there, but okay. So this is the type of interpretability that we would like to create and that are under investigation, such that also here we could find the importance of the different parameters in sports medicine. So to summarize, there is an enormous potential behind artificial intelligence. The first successes are promising, but in several papers, we are not yet there. It must be further developed. Ideally, would we really, and that's what Bernd has been hinting at, our S-training network, which is based on a sound collaboration between data scientists and sports scientists, because that's what we need in order to succeed. And yeah, another interesting data that I just wanted to mention, there is a lab in Rennes, in France, that is working with virtual reality system, which is also a nice way of creating further data. And yeah, this is for those who want to have a soft introduction to artificial intelligence and what can be done with it. Again, with Romain and with some other colleagues, we wrote this editorial, Artificial Intelligence and Machine Learning, an Introduction for Orthopedic Surgeons. A second editorial in the same journal is currently under preparation, where we try to explain it in clear terms, so as to also motivate for its usage. Thank you very much for your attention.